Okay, the interaction between electrons also includes the idea of electron shielding, which, we will come to see has a lot to do with things like the sizes of atoms and ions also. um, and it occurs because in atoms with more than one electron, each electron experiences an attractive charge from the nucleus, because the electrons are negative and the nucleus is positive. So that's an attractive charge. But also, it experiences charges of other electrons, which are repulsive because the other electrons are negative, like the electron you're interested in. So the interactions with the other electrons effectively shield the electron you're interested in from the attractive charge of the nucleus. And what that means is that for any given electron in an atom, it probably experiences less than the full attractive charge of the nucleus. And that's especially true if there's at least one shell of electrons between the electron of interest and the nucleus. And this phenomenon basically begins with lithium, which has 3 electrons. In order to have a shell of electrons between the electron of interest and the nucleus, you would normally need to have at least 3 electrons total. And so that would be from lithium on. The electrons in the same shell as the one you're interested in don't really have very much shielding effect. They can push themselves and other electrons in that shell a little further apart, which can take them a little further away from the nucleus, and that can affect the amount of attraction that the nucleus has on those electrons. But they don't really affect the electron you're interested in through shielding, not directly anyway. Okay, so in effect, the outer electrons will experience a reduced nuclear charge. Okay, and what that is called is the effective nuclear charge. Or Z effective. Z, of course, being the atomic number, which for any given element tells you how many protons there are in the nucleus. So Z, the atomic number for any given element, is also the charge on the nucleus. And so when we say Z effective, what we really mean is the effective charge on the nucleus. That is the amount of charge from the nucleus that's actually being experienced by outer electrons. The book chooses not to tell you how to calculate the effective nuclear charge just yet, but might as well let you in on the secret. We'll be seeing it later and doing more with it then. And so it takes the form of the total charge on the nucleus, which is just the same as the atomic number, minus the number of electrons in shells that are closer to the nucleus than the electron that you're interested in. So that would not include electrons that are in the same shell as the electron you're interested in. If the electron you're interested in is a valence electron, that is one of the electrons in the outermost shell of the atom, and in most cases it will be because those are the electrons that are involved in bonding, then what we're talking about here would be the core electrons of the atom. Normally when you talk about the core electrons of an atom, you're talking about all of the electrons except the ones in the outermost shell. But we'll get that in more detail later, so you don't really have to worry about that too much right now. There is also a concept known as penetration. And that is about the distribution of electrons in the various types of orbitals. If you look at the distribution for the types of orbitals that's given in the book, you'll notice that some of them have a little bump that's actually closer to the nucleus than the main bump, which is where the electrons for that type of orbital would be most likely to be found. Some of them have a little bump that's closer to the nucleus, which means there's a chance, not a huge chance, but a significant chance of you finding that type of electron at that distance from the nucleus. And that distance from the nucleus sometimes is closer not only than the area of greater probability of finding an electron for that type of orbital, but sometimes it's actually closer to the nucleus than types of orbitals that are nominally lower in energy than that type of orbital. And so that's what we're talking about with penetration. If an outer electron penetrates into the cloud of inner or core electrons, the nuclear charge experienced by that type of electron increases, because some of those electrons are actually closer into the nucleus than you would expect them to be. And that's because there are fewer other electrons between it and the nucleus than you would expect. And of course, according to Coulomb's law, this means lower energy. And this is related to also, as I was saying, the spatial distribution of electrons. Okay, so that's a mouthful. Electron spatial distribution and sublevel splitting. Yes, quantum mechanics is definitely the fun part of chemistry. The splitting results from the three-dimensional distribution of electrons within an orbital type. Within a Okay, in n equals 2, it turns out that p orbital electrons actually tend to be found closer to the nucleus than s orbital electrons. Okay, but the 2s orbital has lower energy if the 1s orbital is occupied. Interestingly enough, if the 1s orbital is not occupied, then the p orbitals would have lower energy. Fortunately, the 1s orbital is almost always occupied, so we don't really have to worry about that. This is due to potential penetration close to the nucleus by 2s electrons. And there is a diagram in the textbook on page 321 that shows this better than I could draw it. So I am going to look it up. Okay, so here's a diagram of the distribution of the probability for finding electrons. You notice that for 1s electrons, you have a huge likelihood right close to the nucleus, and then it tails off fairly quickly. For the 2s electrons, you actually have two bumps. There's one that's here very close to the nucleus, kind of within the area normally occupied by 1s. So there is a significant chance of finding 2s electrons very close to the nucleus, but the main distribution of 2s electrons is further out. Actually, the main distribution for 2p electrons is closer to the nucleus than the main distribution for 2s electrons. But because of this little hump here, that kind of lowers the energy of 2s electrons overall on average. And you usually end up with 2s electrons being lower in energy on average than 2p electrons. And here's a broader view of the penetration toward the nucleus down here. All right. Okay. And so there's less shielding for the 2s electrons here. And the 2p orbital electrons don't penetrate like that. And because of that, the 2p electrons don't get their energy lowered by being closer to the nucleus. And the shielding is still in full force, and so they end up being higher in energy overall. And it turns out that the relationship between the s and p orbitals for other shells is similar. In shells starting with n equals 3, the relationship between the s and p orbitals is actually similar to what it is in the second shell. And the d orbitals penetrate less than the s and p orbitals, so their energy would be higher than s and p. And it's because of lack of relative penetration. Also because of this, there are some anomalies in the relative energies of orbitals. For example, it turns out that 4s orbitals are slightly lower in energy than 3d. And so 4s will fill first. And that's actually the same for 5s versus 4d, and so on and so on and so on, all the way out. Basically, the s orbitals of the next shell will be slightly lower in energy than the d orbitals of this current shell that you're working on. In fact, the separation in energies between types of orbitals actually gets smaller as the principal quantum number increases. So in terms of energy, the orbitals get closer and closer to each other as they move further out from the nucleus. That's also shown on page 321, right here. So you see how far apart 1s and 2s are, and then there's a fair distance between 2s and 2p, and between 2p and 3s and 3p even. But now when we get to 4s, you notice things are getting pretty close up here. 4s to 4p, pretty close. And then you notice that actually 5s is way up here and 3d is down here. And so on. And so they're getting closer and closer together, and you end up with some overlap between them that you might not otherwise expect. Okay, let's see. So next we come to electron configurations for ground state atoms with more than 2 electrons. We've already seen the first 2. Okay, the electrons in an atom, we've already established this. They normally occupy the lowest energy position available. And this is the ground state. And normally, if you're asked to write an electron configuration, it's safe to assume that we mean the ground state, unless we say otherwise. Actually, it's pretty much has to be the ground state because there's practically an infinite variety of possible excited state electron configurations for any given element, even hydrogen. There are any number of different shells that one electron can jump to, and any number of different orbital types within that shell. So even for hydrogen, we're pretty much going to have to assume that anytime you're asked to draw or write up an electron configuration, you pretty much have to assume that it's a ground state, unless you're given some specific information on how it's excited. So we can now detail the arrangement of electrons in an atom, since we know the relative energies of the orbitals. And again, the electron configuration is just built up from the lowest energy orbitals on up until you run out of electrons. And that again is the Aufbau principle. So each successive electron goes into the lowest energy space available. And when a given orbital is full, the next electron goes into the next lowest energy position available. And so on, again, until you run out of electrons. And so for some examples, we could start with hydrogen. We've already seen that one, so that shouldn't be too bad. That's 1s1. And you could draw it like that if you want to. Helium with 2 electrons, 1s2. And there you go there. Remember, the electrons have to be opposite spin if they're in the same orbital with each other. This method, the graphical method of writing electron configurations, shows what spin each electron has. The compact way of writing it, like 1s2, does not show you what the spins are. You just basically have to assume that if they're able to be in the same orbital together, then they must be of opposite spin. Next, we would come to lithium with 3 electrons. When you get to 1s2 with 2 electrons, you've filled up the s orbital, and the s orbital is the only type of orbital that exists in the first shell. So you've also filled the first shell. The third electron ends up having to go into the lowest orbital in the second shell. So it's going to be 2, and it's going to be an s-type orbital, and there's only 1 electron left to go into it, so that's 1, 2s1. So 1s2, 2s1. Okay. And so that's 1 electron in the 2s orbital. We can then move on to beryllium with 4 electrons. There's a vacancy in the 2s orbital, and so that's where the 4th electron goes. And so now we have this for an electron configuration. Okay, we have next, let's see, beryllium boron. Okay, shell number 1 is filled. Whoop. The s orbital, in shell number 2 is filled. And so the 5th electron has to go to now the p orbital in shell number 2. And there will be a total of 1 electron in p. the 2p orbital. But remember, there are 3p type orbitals in any given shell that has them. And so we have the 1s orbital filled, the 2s orbital filled, and the first electron will go into one of the 3p orbitals. Doesn't really matter which one you put it in. And it doesn't really matter whether you draw it spin up or spin down, as long as there's only one. The next element is carbon with 6 electrons. And things get interesting here. Because, well, we got 1s2, 2s2. We know how that goes. We've got 2 electrons in the p orbitals of shell number 2. We know where the first one goes because we already drew that in up above. The question is, where does the second one go? Does it go in that same orbital and double up with the first one? Or does it get a place of its own? The answer is it gets a place of its own. Even though, as I mentioned, even if you have 2 electrons with opposite spins, there's still a little bit of repulsion there, and it takes some energy to force them into the same orbital together. And so they would definitely prefer to get their own orbital rather than having to share it. If the electrons go into separate orbitals, then they will have the same spin, actually. Well, that is separate orbitals of the same energy. So like the p orbitals, the degenerate type orbitals, like we said the other day. When you have multiple orbitals of a given type and they all have the same energy, like the 3p orbitals in any given shell, the second electron goes into one of the other p orbitals. It doesn't double up with the first one, with the first electron, and it will have the same spin, because that is a slightly lower energy proposition than having 2 electrons in 2 different orbitals with different spins. I don't know why, but it just is. And this is an example of Hund's rule of maximum multiplicity. Our book just calls it Hund's rule. I'm kind of disappointed. I like saying maximum multiplicity. Okay, so Hund's rule of maximum multiplicity. And what that says is that degenerate orbitals will fill singly with electrons of the same spin before electrons double up. And that's Hund's rule of maximum multiplicity. All right, the next element we come to would be nitrogen, with 7 as its atomic number. Okay, so 1s2, 2s2, 2p3. Okay, we have 1s2, 2s2, 2p3. That means that each of those 3 electrons gets its own orbital among the 2p orbitals. And the next one is where it gets interesting. That's oxygen, with an atomic number of 8. One s2, 2s2, 2p4. So we fill the electrons as 1, 2, 3, 4. Now one of the one of the orbitals has 2 electrons in it, but the other 2 still have single electrons. Okay, and then we can just keep adding electrons, and we eventually come to neon at the end of that row. I guess I only skipped one element. And where we have 1s2, 2s2, 2p6. So there's your 1s2, 2s2, 2p6. Turns out when you have entire shells that are completely filled, that results in a great deal of stability for an atom or an element. Here we filled up n equals 1 because remember n equals 1 consists entirely of that single s orbital. That's filled. We filled up n equals 2, which consists of an s orbital and 3 p orbitals. They're all filled. So we've got 2 completely filled shells of electrons. That means neon is really stable. And neon is one of the noble gases. So that makes sense. If we look back above, there's one other element we've done so far that also has a filled shell of electrons, and it's this one right here, helium. Oh, sorry. Wow, I put 2 electrons in for hydrogen, didn't I? Yeah, scratch that out if you actually did that. If you noticed the mistake when I made it, congratulations. Yeah, for helium, the first shell consists only of that s orbital. So that's also a filled shell. And helium is also a noble gas. And so if you go through the elements and write out all their electron configurations, every so often you'll keep coming back to elements that have completely filled shells of electrons, and those are the noble gases. And those are the ones that are really, really stable. The book lists out the orbital filling order because the orbitals don't always fill in the way that we would expect them to. As we saw with that diagram that showed the relative energies of the different orbitals, their orbitals don't always relate to each other in terms of energy the way we would expect them to. So it is true that the next electron, when you're doing an electron configuration, the next electron will always go into the lowest energy spot available, but the lowest energy spot available is not always what you think it is. And that's because of the weird way in which the orbitals sometimes relate to each other in terms of energy. So the order goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. And they present that as if that's something that's easy to remember. It's actually not. There is a much easier method to remember the order of filling of electrons, which I will show actually in the next segment of the video because we're over 30 minutes already. So I'll be right back.